The sun unleashed a chilling spectacle. A colossal gash tore across its fiery surface, spewing a torrent of plasma straight toward Earth. At that very instant, the enigmatic interstellar comet 3I Atlas vanished from every telescope's gaze. Simultaneously, Mother Earth shuddered with a powerful earth. The mystery gripping everyone's thoughts is what just happened. Was Comet 3I Atlas obliterated or transformed into something new? And if it reappears, what strange form might it take? As this cosmic enigma fades into the shadows, another celestial marvel steals the stage. Comet Lemon, an ancient icy wanderer predating civilization itself, blazes across our skies. Here's why the next 2 weeks will be absolutely pivotal.
And that eerie green glow everyone's buzzing about. It flared up at the precise moment it shouldn't have been possible.
Meanwhile, in China, physicists have pulled off a feat straight out of a sci-fi thriller, an unbreakable, unhackable communication network that exposes every secret. Don't blink, because before we wrap up, we'll unveil the must-know cosmic dates you can't afford to miss, including one flying under the radar that everyone should be buzzing about. If these enigmas have your pulse racing like they do mine, don't just sit there, take charge, smash that like button, hit subscribe, and stay glued as these mind-blowing stories unfold in real time.
Walk you through exactly why Loeb urges you to take that vacation before it hits.
Leave a comment below with your location, the local time, and your honest take. Are we being fed the full truth about these earth-shattering discoveries? Want to fuel this community's growth? Share this video on X, Facebook, Reddit, or your group chats. Every share, comment, and click powers our pursuit. We deeply appreciate your solidarity in this quest for answers. Part 1: The Vanishing Act. The sun unleashed a spine-chilling spectacle in October 2025, sounding a cosmic alarm that went unnoticed by most. Scientists vigilantly observing our star were gripped by mounting dread as a colossal transquatorial coronal hole tore violently across the solar surface. Papers published in the last 2 weeks.
Instead, he begins with a single staggering figure, 20 kilometers. That's the estimated diameter of Atlas, calculated from its blazing brightness when it was first spotted.
A jagged tear in the sun's magnetic field gaped like a cosmic wound, hemorrhaging invisible energy into the void of space. This was no ordinary solar event, no mere spark for dazzling auroras or minor satellite glitches. The chasm was monstrous, stretching across both the northern and southern hemispheres of the sun in a single awe-inspiring breach. 456 metric tons per day, enough to fill an Olympic swimming pool daily for months. A rare and ominous cosmic event unfolded its full consequences, still shrouded in mystery. A ferocious solar wind unleashed through a gaping tear in the sun's magnetic shield surged at a staggering 700 kilometers. Picture a hurricane where every air particle roars at nearly 1.5 million mph. This relentless stream of charged particles, protons and electrons ripped from their atoms, hurtled toward Earth like a celestial fire hose. The solar wind's magnetic polarity aligned perfectly with Earth's field, locking into the exact configuration for maximum coupling, a fierce surge of energy from the sun's cosmic breath flooding our planet's magnetosphere. Geophysicists raced to forecast the fallout, while urgent warnings flashed to power grid operators. Our cosmic twins, forged in the hearts of dying stars, expelled in supernovae, and traveling together in every comet, asteroid, or space rock we've ever studied. The ratio might shift, but both are always present. Always. Satellite controllers braced for potential chaos, readying for malfunctions. Aurora chasers clutching their cameras raced north, eager for a solar onslaught that would ignite the sky with indescribable hues. Yet at that precise moment, something else erupted. Industrial nickel refinement facilities on Earth, specifically the carbonyl process. In that process, nickel ore is exposed to carbon monoxide under precise conditions, forming nickel, a phenomenon that transformed this solar flare-up from a mere space weather event into a profound cosmic enigma. Comet 3I Atlas, only the second confirmed interstellar wanderer ever spotted in our solar system, vanished behind the sun's blazing veil. One moment it gleamed faintly, a ghostly streak of light, tracing an orbit born in a distant star system, bearing ice and rock forged in alien clouds around a sun forever beyond our sight. The production rate, in a fleeting instant, it vanished into the sun's blinding glare, engulfed by the star's ferocious brilliance, invisible to every telescope on Earth and beyond. The timing was uncanny, impossible to dismiss. Earth's magnetic field reeled under the onslaught of the swiftest solar wind in months, while at the same moment, our sole interstellar messenger went dark, obscured by the very source of that cosmic assault. Messenger to spread the word. Thank you, cosmic gardeners, for joining this journey.
To peg it as enormous.
Scientists meticulous by nature and trained to steer clear of hasty conclusions repeatedly caution that correlation does not imply causation. They chose their words with precision when reporters probed whether these events might be linked. Then the ground began to quake. Bye-bye. It was executed with surgical precision, as if choreographed by some unseen intelligence. For months, this enigmatic object has been unleashing a torrent into the void, 144 metric tons of water every hour, laced with nickel cyanide and ionized plasma. This isn't random space debris. It's the precise molecular recipe for metalloproteins, those uncanny hybrids where biology and technology can. Mars, it seems, just received an express delivery from another star system. The chemistry is flawless, the timing almost too perfect to be chance. What if this was the plan all along? This is a thought experiment, yes, but one anchored in hard science with facts that demand attention. If this sparks your curiosity as much as it does ours, hit that like button and subscribe for more. Drop a comment below, tell us where you're tuning in from the local time, and whether you. What if 3I Atlas is seeding Mars? Picture this, an object from another star system screaming through space at over 200,000 km/h brushes past Mars in what astronomers call a near miss. But this is no ordinary space rock. It's a delivery vehicle carrying the raw ingredients for something extraordinary. A bold ex-user put it bluntly, 3I Atlas is a seed, not a poetic metaphor, but a literal. Since we first spotted 3I Atlas in July, it's been hemorrhaging water at a staggering rate. The Neil Gerald Swift Observatory clocked its outflow at 40 kilos per second, 88 pounds every single second. Imagine a fire hose cranked to full blast running non-stop since early summer. The numbers are almost surreal, 144 metric tons per hour, 456 metric tons per day, enough to fill an Olympic-sized swimming pool every. In late August, the KEK Observatory in Hawaii turned its instruments toward this cosmic wanderer, expecting the usual suspects, typical cometary chemicals kicked up by solar proximity. What they found defied every model of natural cometary behavior. Strong, unmistakable nickel emissions, but with no trace of iron. This is a cosmic anomaly. Here, nickel ore is exposed to carbon monoxide under precise conditions, forming nickel tetracarbonyl, which breaks down to yield pure nickel. It's a process we've mastered since the early 20th century. And now it's happening on an interstellar comet, or as Avi Loeb suggested in his Medium post, perhaps not naturally at all. Second 2I Borisov in 2019 felt more familiar, a comforting ball of ice and dust behaving like the predictable comets we know, adhering to the reliable laws of physics.
Coincidence. The trajectory is random. The alignment's luck. The timing just happened. But when you keep rolling sixes over and over, you start to wonder if the dice are loaded.
But the nickel is only half the equation. The other half is cyanide, specifically hydrogen cyanide HCN, gushing from 3I Atlas's coma in escalating quantities as it approaches the Sun. The Very Large Telescope in Chile tracked this in real time through August and September, measuring 20 GUS by late August. By mid-September, the James Clerk Maxwell Telescope recorded 1.5x 1025 molecules per second. Now let's talk about cyanide. Yes, it's a poison, but it's also one of the most critical prebiotic molecules known to science. Cyanide is a builder capable of assembling the precursors of life, amino acids, nucleotide bases, the scaffolding of metabolism under the right conditions. In the 1950s, Stanley Miller and Harold Urey ran electricity through a mix of simple gases, including hydrogen cyanide, and produced amino acids, the building blocks of proteins. In the 2000s, researchers at the Scripps Research Institute. Then there's nickel. Beyond being a metal, it's a biological catalyst embedded in some of the most ancient enzymes known to science. Hydrogenases, which split hydrogen molecules to release energy, and carbon monoxide dehydrogenases, which convert CO2 into usable carbon compounds, both rely on nickel at their core. These enzymes were the workhorses of primitive metabolism, enabling early life or proto-life to extract energy from hostile environments. Together, water, cyanide, and nickel form this cosmic cocktail spewing from 3I Atlas as it grazes Mars is what an ex-user called the makings of metalloproteins hybrid molecules, where metal cores blur the line between biology and technology. They're not wrong. The chemistry is too precise, the delivery too timely to dismiss lightly. Is 3I Atlas planting the seeds for a new form of life on Mars? One that merges the organic and the mechanical? So what do you think? Are we watching the dawn of something entirely new? Drop your thoughts in the comments. Where are you? What time is it? And do you believe this could be the birth of a new life form? Share this on X, Facebook, Reddit, or Messenger to keep the conversation alive. Thank you, Cosmic Gardeners, for joining us on this wild ride into the unknown.
Drifter, but something with purpose, something engineered.
Trajectory calculations revealed the telltale signature of a hyperbolic orbit, an eccentricity greater than 1, indicating this object wasn't bound to the Sun. It had come from somewhere else. And after its close approach to our star, it would continue on its path, departing back into the vast cosmic ocean between stars. The orbital energy didn't match anything native to our solar system. This was interstellar. What if they're not carbon-based life? The astronomy community mobilized swiftly. Telescope time, typically scarce and scheduled months in advance, was suddenly made available. Spectroscopy. The analysis of light reflected or emitted by the comet became the top priority. What was this thing made of? Did it carry the familiar mix of water, ice, carbon dioxide, ice, and organic molecules that define comets formed within our solar system? Or would its composition reveal an alien chemistry with elemental ratios hinting at formation conditions around a different kind of star? Early data suggested
Told a different story of what we expect to find drifting through the galaxy.
a baffling mystery unfolded. The radiance of Comet 3I Atlas defied astronomers' predictions. Typically, comets blaze brighter as they near the Sun, tracing a predictable arc, driven by the escalating sublimation of ice. As solar heat surges, water ice begins to sublime, transforming directly from solid to gas when sunlight warms the surface to roughly 200 degrees Kelvin. fourth state a dynamic soup of ions and free electrons. This plasma carries more than raw materials, it holds information. Not like a radio signal, but in its structure. The other volatiles, such as carbon monoxide and carbon dioxide, transform into gas at even lower temperatures, sparking activity at far greater distances from the Sun. The brightness curve of Comet 3i Atlas revealed intriguing pauses with periods of flattening where its glow didn't intensify, as models forecasted only to be followed by abrupt surge. The coma, that hazy veil of gas and dust enshrouding the comet's nucleus, glowed eerily faint in certain observations. The dust output was surprisingly sparse for a comet of its stature. Some scientists theorized that the nucleus could possess an exceptionally high density dominated by rock, rather than ice accounting for its subdued activity. The science is real, the question's urgent. If this grips you, smash that like button and subscribe. Tell us in the comments, where are you, what's the time? And do you think we're watching the birth of a new life form? Share this on X, Facebook, Reddit, or Messenger to fuel the conversation. Some argued the contrary, proposing that the comet's nucleus was remarkably porous, resembling a loosely bound rubble pile, barely held together by feeble gravity. This fragile structure triggered the ice to sublimate in erratic, explosive bursts, rather than a steady release. Then there were the mysterious, non-gravitational forces at play. Could be doing something similar, but on a grander scale. It's not just dumping chemicals. It might be carrying a template for organization, a set of initial conditions that could nudge whatever forms on Mars toward a specific kind of complex. Comets defy the neat, predictable Keplerian orbits dictated solely by the Sun's gravitational pull. As ice vaporizes from their nucleus, it unleashes powerful jets of gas functioning like miniature rocket thrusters that nudge the comet off its expected trajectory. These subtle yet detectable non-gravitational accelerations inject a thrilling uncertainty into forecasting a comet's precise position at any moment. Of a clear mission build. They'll construct solar arrays, habitats, and resource extraction systems, laying the foundation for human colonies. But they won't stop there. According to Elon Musk's public statements, these robots will also build more robots, self-replicating machines that learn and adapt.
Out of gas and dust, amplifying its glow, making it appear larger than it is.
For Comet 3i Atlas, these disturbances proved exceptionally challenging to predict. Its orbital calculations required constant refinement, with error margins shifting unpredictably, leaving astronomers grappling with growing uncertainty about the exact timing and location of the comet's reappearance from behind the Sun's glare. Some observations even suggested potential fragmentation before it vanished entirely. Cyanide water, the exact ingredients for metalloproteins, those hybrid molecules, where biology and technology blur. On Earth, metalloproteins are indispensable. Hemoglobin needs iron to transport oxygen, chlorophyll relies on magnesium for photosynthesis, and vitamin B12 hinges on cobalt. Remove the metal and the biology. Comet nuclei, delicate and loosely knit amalgamations of ice and rock, are prone to shattering under the strain of thermal stress or tidal forces. When a comet splinters, it frequently spawns a trail of smaller fragments, tracing near-identical orbits, occasionally appearing as multiple glowing knots within the coma. Observations of Comet 3i Atlas revealed tantalizing hints of asymmetry and elongation, subtle signs that its nucleus might have been unraveling. If the comet...
This idea, known as deliberate trajectory insertion, unsettles astronomers because it's nearly impossible to prove without unmistakable evidence. Signs of artificiality might include non-gravitational acceleration, beyond what cometary outgassing can explain, active trajectory corrections, or emissions betraying technological origins. So far, 3I Atlas has shown no such conclusive signals, though whispers of unusual behavior persist, as noted in earlier discussions.
It displayed no shimmering coma, no trailing dust tail, nothing to unmistakably mark it as an icy wanderer. Yet it surged away from the sun with an acceleration that defied the pull of gravity alone. The most plausible cause, comet outgassing, but not from ordinary water, something far more exotic, like carbon monoxide or molecular nitrogen. These volatile substances would sublimate silently, leaving no visible dust in their wake. Witnessing the birth of something new on Mars. Drop your thoughts in the comments.
Yet there's a counter-argument. We could be overinterpreting the data. The galaxy is vast, home to trillions of objects adrift in the interstellar void. Some will inevitably have origins too ancient or scrambled to trace their histories, erased by billions of years of gravitational chaos. 3I Atlas's link to Sagittarius might be pure coincidence, its untraceable orbit, a consequence of extreme age rather than intent. Human minds are wired to seek patterns to weave meaning from randomness, but science demands skepticism. Assigning purpose to what could be a fluke risks veering into speculation. After all, 2I Borisov fit neatly into natural models, and even Oumuamua, despite its oddities, remains plausibly natural. Perhaps 3I Atlas is simply older, its path more convoluted, its connection to Sagittarius, a quirk of chance that feels profound, but means nothing. Still, the pattern gnaws at us, refusing to be dismissed. The dilemma lies at the heart of this investigation, a riddle as inescapable as a black hole's gravity. Is 3I Atlas a drifter so ancient that its story has been obliterated by time? Or is it something more, a probe placed on a calculated path? Guided rather than random orbital forensics alone cannot resolve this, as both scenarios produce the same signature and object with no clear parent star tracing back to a direction rather than a place.
The geometry of solar conjunction, when an object slips behind the sun's blazing veil from Earth's perspective, carves out a maddening observation gap that can stretch for days or even weeks, dictated by the object's path and radiance. For a dim comet, already flickering with eerie, unpredictable behavior, this gap transforms into a cosmic black box, a mysterious void, where anything might unfold, leaving us utterly blind to its secrets. The comet might be crumbling into oblivion. It could be blazing with breathtaking brilliance. Or perhaps it remains whole, shrouded too closely within the sun's blinding glare to be seen. We won't know until it reappears, if it reappears at all. Scientists scrambled to model its fate, piecing together predictions based on guesses about its nucleus size and makeup. If the comet's core is large and predominantly rocky, thermal simulations suggest it could endure shedding only a fraction of its mass. But if it's a smaller, icy body, the searing heat near perihelion might reduce it to nothing more than a fading wisp of gas. Astronomers dubbed it the invisible interstellar traveler, a mysterious visitor from another star system, concealed behind the sun's relentless glow, beyond the reach of every telescope humanity has crafted. It's either defying the odds or disintegrating, and we're left powerless, waiting in suspense to see what, if anything, will emerge when the cosmic alignment finally permits a glimpse. The anticipation feels like an eternity squeezed into mere days. Nucleus. A brief burn, a course correction, veiled by natural outgassing.
But if there's even a sliver of a chance, it's something more failing to investigate thoroughly. Could be a monumental oversight.
Part 3. When solar wind collides with alien ice. The sun is no gentle giant. We cherish it as the radiant, life-sustaining star that bathes Earth in warmth and light, nurturing our world. Yet peel back its serene facade, and the sun reveals a savage nature, a seething, roiling sphere of plasma where temperatures soar to millions of degrees and magnetic fields coil like tightly wound springs brimming with volatile energy. When those springs unleash, the consequences can be catastrophic for anything in their path.
Let's keep peeling back the layers of this cosmic enigma.
In October 2025, a coronal hole tore open on the sun's surface, sending a shiver through the solar physics community. These enigmatic coronal holes are regions where the sun's magnetic field unfurls into space, no longer tethered to its fiery surface. These open field lines become cosmic superhighways, channeling solar wind streams of charged plasma racing into the solar system at breakneck speeds, at a specific point in its trajectory. For those 2 points to align, given the 7-month journey from Jupiter's orbit, where the object first became visible, the launch timing had to be impossibly exact. Not just skimming the ecliptic plane, not just passing near Mars, but passing near Mars when Mars was there. Planets don't loiter. They move.
The odds of 3-eye Atlas pointing to Sagittarius by chance seem plausible at first glance. The sky is divided into 88 constellations, and Sagittarius, being one of the larger ones, spans a significant portion of the celestial sphere, perhaps a 5 to 10% chance of any random trajectory aligning with its borders, depending on how precisely you define them. But the plot thickens when you consider the wow signal, the most compelling SETI candidate ever detected, which also originated from this exact region in 1977.
They lack a magnetosphere to shield them from charged particles, leaving their coma vulnerable to the relentless solar wind. This torrent of energy crashes directly into the comet's halo of gas and dust, where bizarre physics takes hold. Solar ultraviolet radiation ionizes the coma's gas, transforming it into a vibrant swarm of electrically charged molecules. On his scale for anomalous objects, not proof, not even strong evidence, but peculiar enough to demand. These ions, now sensitive to magnetic forces, interact with the solar wind's embedded magnetic field lines, which wrap around the comet like a cosmic cape. The result is a mesmerizing magnetotail, a dynamic structure born from the dance between the solar wind's magnetic field and the comet's ionized gas. Small precursor probe from 3-eye Atlas in August or early September give it a modest velocity nudge, and by October, this radiant tail stretches millions of kilometers downstream, trailing away from the sun, shimmering faintly with the glow of ionized carbon monoxide and other vibrant molecules. Far from a static feature, the tail dances dynamically, rippling and fluttering under the turbulent forces of the solar wind. At times, dramatic disconnection events unfold, where the tail snaps off completely only for These cosmic interactions are observable from Earth, with specialized instruments offering tantalizing clues about the solar wind's behavior and the comet's gas production rate. But what happens when a comet already strained by the scorching heat near perihelion collides with an exceptionally fierce solar wind? History unveils some awe-inspiring and terrifying spectacles. Mars lacks a global magnetic field, its core having cooled billions of years ago, but it retains patches of crustal magnetization, especially in the southern highlands. It also has an In 2012, astronomers discovered Cometon, a celestial wanderer poised to blaze with breathtaking brilliance. Yet in 2013, as it swept perilously close to the sun, its anticipated glory unraveled. Solar-observing spacecraft captured its dramatic journey entering the perihelion region as a radiant beacon only to emerge, defying all odds. Comet Lovejoy, a daring sun grazer, skimmed a mere 140,000 kilometers from the solar surface in 2011. Despite dire predictions of its destruction under crushing thermal and tidal forces, it emerged triumphant. Stunning images revealed its tail stretching millions of kilometers post-perihelion, a radiant stream fueled by torrents of gas erupting from its superheated nucleus, a testament to its astonishing resilience.
Dust.
The astonishing survival of Comet Lovejoy defied all expectations, leaving scientists scrambling to unravel the mystery. A unique blend of its nuclear size composition and structural resilience enabled it to withstand scorching temperatures that should have obliterated it entirely. Meanwhile, 30 Sinu Atlas ventured into a perilous zone where the sun's influence reigns supreme, navigating this treacherous region during an unusually ferocious solar windstorm. Each anomaly might be explainable alone. Together, they're harder to dismiss. And the Mars Reconnaissance Orbiter wasn't the only asset watching.
Either extraordinarily lucky or meticulously planned. A few in quieter corners entertain the artificial hypothesis. Though they hesitate to publish such ideas, risk professional ridicule without ironclad evidence. They run private calculations, asking what a deliberately engineered trajectory would look like and whether the data fits. The astronomical community is divided, cautious aware that this could be the most monumental discovery in human history, or a colossal misstep, chasing a rock that's just a rock.
Mainstream astronomers remain skeptical, asserting that conventional physics sufficiently explains observed phenomena without invoking exotic electrical effects. Yet advocates of the electric model point to striking evidence such as abrupt disconnection events in comet tails and sudden dramatic brightness shifts as compelling signs that electrical processes are at play. Because we're here to see them. But the precision is undeniable. In nature, such precision signals either staggering luck or an underlying mechanism. The hypothesis ventures deeper into uncharted realms, proposing that intense solar wind events could trigger charge separations within a comet's coma, potentially sparking explosive disruptions or abrupt trajectory shifts far beyond what mere outgassing could explain. Yet the evidence supporting these bold claims remains fiercely debated. On August 24th, when the Keck Observatory in Hawaii aimed its the theoretical framework remains unfinished, yet its ideas ripple through discussions driven by their bold attempt to account for observations that defy conventional models. When Comet 3I Atlas mysteriously vanished amid a massive solar wind event, advocates of electric comet models seized the moment, viewing it as a striking validation of their theories. When a massive star exhausts its fuel, its core collapses, triggering a supernova. In that cataclysm, mainstream astronomers witnessed a cascade of events dismissed as a tragic, yet purely coincidental convergence. The mystery deepens with our ignorance of Comet 3I Atlas's true nature. Sparse spectroscopic observations before its vanishing act offered only fragmented clues, leaving its composition a puzzle. It might be dominated by water ice akin to typical solar system comets, or perhaps carbon monoxide ice which vaporizes. A typical comet's core is a complex blend, each element reacting uniquely to the sun's scorching heat and relentless solar wind. If the nucleus is extraordinarily porous, resembling airy aerogel with a density scarcely greater than the surrounding coma's gas, thermal waves would burrow deep, warming, hidden ice reserves. If the nucleus is shrouded in an insulating dust mantle across most of its surface, gas production would surge from a handful of active regions, unleashing powerful jets that might whip the nucleus into a frenzied spin or twist its rotation in erratic, unpredictable ways. If the nucleus is a contact binary, two lobes barely clinging together under feeble gravity, tidal forces and thermal stress could wrench it apart. near the nucleus. Here's how it works on Earth. Take nickel, often impure and mixed with other elements, and expose it to carbon monoxide gas at modest temperatures, around 50 degrees Celsius. The nickel reacts with CO to form nickel tetracarbonyl. In this cosmic drama, the sun emerges as a formidable gatekeeper, a destructive force that ruthlessly challenges every object daring to traverse the inner solar system. Interstellar comets born in alien environments with potentially unique structural properties compared to our solar system's comets might prove especially vulnerable, or perhaps more resilient, forged in conditions that rendered them tougher. The truth remains elusive until we witness what survives this celestial gauntlet. The parallel to Comet Shoemaker-Levy 9 offers a compelling lesson: temperatures and pressures. So if the carbonyl process is in 1992, a cosmic drama unfolded as Comet 3I Atlas ventured too close to Jupiter, only to be ripped asunder by the planet's relentless tidal forces. Shattered into over 20 fragments, these remnants later plummeted into Jupiter in a breathtaking cascade of collisions. The tidal disruption occurred because Jupiter's immense gravity gradient stretching across the comet's diameter overpowered its own feeble self-gravity, tearing it apart with ruthless precision. To occur naturally and with enough efficiency to completely suppress iron emission stretches, the sun's tidal grip, though feeble at the distance where Comet 3I Atlas swept by, could still prove deadly. A comet already battered by thermal stress or earlier fragmentation might crumble under forces that a robust nucleus would effortlessly shrug off. Has the sun just unveiled a chilling secret about these interstellar wanderers? The truth hinges on what we discover when the comet re-emerges from its conjunction with the sun. Deep and chaotic. For the carbonyl process to dominate, you'd need stable pockets at just the right temperature, oases of equilibrium in a system defined by disequilibrium. Possible, perhaps. Likely, that's where doubt creeps in.
Uncanny journey.
Should the enigmatic 3I Atlas re-emerge unscathed, tracing its hyperbolic path with steady streams of gas and dust, the solar wind eruption fades into a mere side note, a fleeting coincidence that ignited curiosity but carried no deeper meaning. Yet if the comet has shattered or vanished entirely, we're confronted with unsettling mysteries. Our interstellar wanderers in the gripping fourth chapter, the cosmic vigil ignites. Astronomers are feverishly circling dates on their calendars, poring over ephemerides and meticulously crafting observation plans for the pivotal moment when Comet 3I Atlas might re-emerge into view. The timeline hinges on a web of variables, the comet's elusive trajectory muddied by unpredictable non-gravitational forces, its brightness, which may have undergone a dramatic transformation, and the observing geometry dictating how far the comet must stray from the sun's glare before telescopes can pierce the celestial backdrop to spot it. Current projections tantalize with possibilities suggesting turning out amino acids at high yield. You'd question the comet is expected to reappear from its solar conjunction in late October or early November 2025, achieving enough angular separation from the sun, as viewed from Earth, to become visible with advanced equipment. Early efforts to spot it will likely rely on space-based observatories, which can more effectively shield the sun's glare compared to ground-based telescopes. Earth's history offers a parallel. Early life didn't invent photosynthesis from nothing. The Solar and Heliospheric Observatory is equipped with advanced coronagraphs that ingeniously simulate eclipses, unveiling the sun's secretive surroundings, where comets often lurk unseen. Meanwhile, Mysterio, the Solar Terrestrial Relations Observatory, deploys 2 spacecraft in solar orbit, capturing unique perspectives that could spot these elusive comets far sooner than any Earth-based telescope. A compound forms near the surface, evaporates, travels briefly, and decomposes. Nickel tetracarbonyl fits perfectly volatile but unstable. It evaporates in a vacuum, moves with the gas flow, and breaks down under solar UV within minutes. The resulting nickel atoms absorb sunlight and fluoresce, producing the observed emission lines. Iron, if present in the nucleus, the Parker Solar Probe. Humanity's boldest venture to touch the sun, traces a daring orbit that sweeps it closer to our star than Mercury itself, plunging through realms where solar winds howl at ferocious speeds and temperatures soar to unimaginable extremes. Should its path align near 3 Atlas during the comet's conjunction phase, the probe's cutting-edge instruments could seize unprecedented data unveiling secrets of the comet in conditions beyond the reach of any earthbound telescope. Metal grains mixed with ice and rock. Comets are dirty snowballs, but their dirt always includes metal, a mix where iron dominates and nickel follows. The Parker Solar Probe's mission is laser-focused on unraveling the mysteries of the solar corona and solar wind, not chasing comets. For it to capture data on a comet, that comet would need to serendipitously drift into the probe's narrow field of view at precisely the right moment, an unlikely cosmic alignment. So far, mission scientists haven't reported any such fortunate encounters, hinting that either the geometry was off or the comet was simply too dim to stand out against the dazzling solar backdrop, leaving Parker's instruments without a trace to detect.
Its surface might be coated in ice and dust collected during its interstellar journey, frost on the windshield, so to speak. As that frost sublimates under solar heat, it creates the expected tail, even if the object underneath isn't a typical chunk of ice and rock.
What will the initial recovery images reveal? In the best-case scenario, the comet emerges as anticipated, possibly a tad dimmer from dust depletion, yet strikingly intact, flaunting a vibrant coma and a flowing tail that signal vigorous ice sublimation from its nucleus. Its spectral signature would gleam with recognizable traces of water vapor, cyanogen, and carbon monoxide molecular hallmarks that vividly affirm the comet's composition. Process. That's proper science measured cautious. The comet's tail, with its length and intricate structure, reveals vital clues about the rate of gas production and the influence of solar wind in the post-conjunction phase. Astronomers would meticulously measure its brightness, comparing it to pre-conjunction levels to determine if the comet shed substantial mass during its perilous closest approach to the Sun. In the most dire scenario, the comet vanishes entirely. The nucleus shattered into fragments too tiny to detect individually or evaporated completely, leaving behind only a faint dispersing cloud of gas too thin to stand out as a distinct entity. While this outcome would be a scientific letdown, it's not without precedent. Block it and cells choke energy production. Halt's death follows swiftly. Yet paradoxically, this killer is also a builder. Cyanide is prebiotic, a chemical that under the right conditions assembles into life's building blocks: amino acids, nucleotides, sugars, the alphabet of biochemistry. Several comets have vanished after daringly close encounters with the Sun, their disappearance serving as a critical clue in unraveling the complex physics of comet fragmentation. Yet between total loss and survival, a spectrum of thrilling possibilities exists. The comet might re-emerge as a cluster of fragments or as a dazzling string of condensations stretching along its orbit, revealing that the nucleus has split, but its pieces defiantly endure. Cyanide production surged by a factor of 600. Exponential growth is a telltale sign. In biology, it signals reproduction bacteria doubling rapidly. In chemistry, it points to autocatalysis.
On the other hand, the engineered explanation beckons with tantalizing possibility. What if 3I Atlas is no ordinary rock, but an interstellar probe deliberately sent to our solar system as part of a galactic network of monitoring devices. Its trajectory calculated rather than random would explain its resistance to orbital reconstruction. Its arrival from Sagittarius, home of the WOW signal, and its timing in an era when humanity is just technologically advanced enough to notice suggest a purposeful design. A subtle communication strategy we're only beginning to grasp.
The comet might have depleted its near-surface volatiles during its close brush, with the sun forming a darkened, hardened crust that halts further sublimation until intense solar heat fractures the crust or erosion unveils fresh, pristine ice. Dormant comets masquerade as asteroids, displaying no vibrant coma or glowing tail, just a stark, rocky surface glinting faintly under sunlight. Occasionally, comets shatter in dramatic fashion, unveiling pristine, volatile-rich material to the sun's rays, triggering abrupt surges in gas production and dazzling brilliance. A splintering nucleus can spawn fresh, active zones, expanding the total surface area that sublimates. If 3 Atlas fragments erupt and ignite simultaneously, the comet that rises from the spectacle could outshine the one that vanished, captivating all who behold it. Catalyst providing the chemical push for complex reactions. On early Earth, before oxygen or photosynthesis, cyanide could have been. Although it exists in a fragmented state, it would probably dissipate rapidly as the tiny fragments exhaust their ice reserves. Spectral diagnostics will be essential. Pre-conjunction observations revealed the characteristic signs of water and possibly carbon monoxide, yet a comprehensive spectral inventory was never fully acquired. Aligned suspiciously with a delivery mechanism, natural or engineered, poised to seed a planet with life's raw. Post-conjunction spectroscopy could unveil a fascinating array of molecular species previously undetected, either due to the comet's limited production of these compounds or because our observations missed the critical wavelengths. Vibrant oxygen emission lines would signal active water sublimation, while CN cyanogen signatures hint at intriguing carbon-nitrogen chemistry unfolding in the comet's coma. Additionally, the presence of sodium and iron lines occasionally glimpsed in comets. Amateur astronomers are vital to the recovery mission. A global network of backyard telescopes delivers round-the-clock sky monitoring, surpassing the capabilities of professional observatories, constrained by limited observing windows and fixed schedules. Should the comet Atlas suddenly flare up or break into widely scattered fragments, these dedicated amateur stargazers could be the first to spot the change. Dropping to 125 degrees at the poles, it lies dormant, frozen in the regolith, potentially for millions of years. It doesn't react or polymerize, it endures. Crowdsourced astronomy is gaining thrilling momentum as advanced digital cameras and powerful software empower passionate amateurs to deliver observations that rival the precision of professionals. A captivating cosmic mystery is unfolding live, inviting anyone with a telescope and clear skies to join the adventure and contribute to unraveling the universe's secrets. Polymerization kicks off. HCN polymer forms, gumming up the unit-clogging filters. Embedded in that polymer are amino acids, nucleotides, and organic precursors. The robot blind to prebiotic, the comet might burst back into view at any instant, provided it endured its fiery trial. Or days could slip by, then weeks with no trace in the sky, until astronomers with heavy hearts accept that 3 Atlas has vanished. Shattered by the sun's relentless blaze, it journeyed so far only to meet its end. The suspense is both tormenting and thrilling in equal measure. No probe was launched to meet this. We're left with no means to actively hunt for it, save for aiming our telescopes at its predicted path and waiting in suspense. All we can do is gaze, speculate, and brace ourselves for whatever might emerge from the sun's blinding glare. A deeper question gnaws at the astronomical community. If the nucleus has vanished, do we still have 3 Atlas comets? Or are we left with mere debris, a scattered veil of dust and gas that once formed an interstellar comet, now no longer a distinct entity? Philosophically, it mirrors the ship of Theseus paradox. If every piece of the original is gone, if a wooden ship has every plank beam and nail replaced over time, does it remain the same vessel? If a comet shatters into 1,000 fragments, each tracing nearly the identical orbit and bearing material from the original nucleus, do they together still form the comet, or has the comet vanished entirely? No formal definition exists to settle this enigma. In chemistry, there's a concept called a catalytic cycle, a series of reactions where the product of one step fuels the next, creating a self-sustaining loop that amplifies a small input into a massive output. It's a question of tradition and practicality, with researchers offering varied responses based on their viewpoints. Yet the question carries weight, because the 3I Atlas embodies something invaluable and unique, a rare glimpse into another star system. Losing it would mean far more than merely losing a celestial object. It's as if we've lost a fragile tether to the boundless cosmos, a delicate thread tying us to the broader galaxy, snapped before we could truly comprehend its significance. A series of massive earthquakes has rocked our planet, setting off every instinctual alarm in our collective psyche, urgently signaling that something profound is unfolding. The prevailing scientific consensus on the link between solar activity and terrestrial earthquakes remains crystal clear and unequivocal. Earthquakes are propelled by the relentless dance of plate tectonics, where lithospheric plates glide atop the convecting mantle, driven by solar activity lacks any credible mechanism to initiate this release. Magnetic fields have no impact on rock formations. Solar wind particles are unable to reach Earth's surface as they are blocked by the magnetosphere and atmosphere. Moreover, the thermal energy from solar radiation is insignificant when compared to the immense internal heat generated by Earth itself. Fluoresce in a similar wavelength range. As cyanide production surged, the comet's appearance shifted from red, dominated by dust, and reflected sunlight, to green, driven by cyanide gas emissions. Every examination of earthquake catalogs searching for connections to solar cycles or specific solar events has uncovered no evidence beyond mere coincidence. Yet intriguing correlations persistently emerge within the data, teasing with patterns that hover just below statistical significance, refusing to fully vanish. It's the molecule that made metabolism possible.
Humanity demanding a coordinated global response.
A cadre of bold researchers, operating on the fringes of mainstream science, relentlessly probes the mysteries of unconventional mechanisms. Might ionospheric turbulence sparked by solar activity alter the electrical characteristics of fault zones? Could minute shifts in Earth's rotation speed or magnetic field alignment, driven by the solar wind's momentum, subtly influence tectonic stress, too faint to measure directly, yet potent enough to nudge a fault teetering on the brink of rupture? Is it possible that magneto-hydrodynamic coupling between the ionosphere and conductive crustal layers channels energy in ways we have understood? Here's your rewritten version, with enhanced style and appeal, but preserving every detail and character. These ideas encounter immense skepticism because extraordinary claims demand extraordinary evidence, and the evidence remains at best circumstantial. Yet the human mind doesn't function by statistical significance thresholds. It operates through narrative, through stories that weave disparate events into coherent wholes.
Task forces to ensure it doesn't spiral out of control. Climate change drives international treaties, summits, and coordinated policy efforts.
When the sun erupts, earthquakes rumble, and a comet disappears, all within a single news cycle. The narrative practically writes itself, even if the physics refuses to cooperate. The interstellar origin of the 3 Atlas adds yet another layer of mystery and speculation. These objects hail from beyond our solar system, from realms we can scarcely imagine, shaped by materials whose composition and isotopic ratios may diverge wildly from the norms of our solar neighborhood.
Radio signal from a distant star which might give us centuries to deliberate a physical visitor in our cosmic backyard demands immediate, decisive action.
They're literally alien in the most precise sense of the word. And humanity has always cast its hopes and fears onto the alien and the unknown. When Oumuamua displayed acceleration that couldn't be readily explained by standard comet outgassing, speculation surged about artificial origins, about alien probes on reconnaissance missions, about technologies that surpass our comprehension.
This is unexpectedly high, hinting at a structure denser or stranger than typical comets.
The simplest explanation still pointed to natural processes, yet the alien probe hypothesis seized the public imagination. It fulfilled narrative desires that sterile scientific papers on carbon monoxide sublimation could never reach. The disappearance of the 3 Atlas during a solar storm invites the same kind of speculation. Did the comet carry something, encode something that marked it as a target? Are we witnessing a kind of cosmic quarantine protocol, the sun acting as guardian obliterating potential threats from interstellar space before they can infiltrate the inner solar system? The scientific absurdity of such ideas does nothing to dull their psychological allure. We crave a universe brimming with mysteries deeper than orbital mechanics and spectroscopy. We yearn for hidden meanings woven into celestial alignments. We want comets to be more than mere dirty snowballs. Date modern biology catalyzing chemistry before cells, genes, or evolution existed. In hydrothermal vents, where hot mineral-rich water meets cold ocean iron and sulfur form microscopic structures.
Some researchers in unpublished observations noted that the coma's density fluctuations and shape appeared almost regulated, as if the outgassing were controlled rather than occurring spontaneously wherever solar heat was strongest. These claims, yet to be peer-reviewed and difficult to verify with ground-based telescopes, remain contentious, but add to a growing list of peculiarities that challenge standard cometry models.
The destruction of 3I Atlas, if that's truly what occurred, becomes the loss of a biological sample, a cosmic library burned before its contents could be read. Meanwhile, more exotic interpretations swirl through fringe communities. Proponents of the electric universe theory view the sun's encounter with the comet as proof of plasma dynamics that they insist mainstream science refuses to acknowledge.
Prepare for both.
They point to the comet's unusual brightness fluctuations, the intensity of the solar wind, and the disconnection events recorded in other comet tales, arguing that such phenomena demand electrical, not gravitational, or thermal explanations. Yet the mathematics behind their models seldom survives rigorous scrutiny. To grow on just hydrogen, their predictions often fail to align with observations, yet the intuitive allure of electricity as a universal force endures. The sheer visual drama of lightning and sparks grants electric universe ideas a resilience that outlives their scientific flaws. And inevitably, conspiracies arise. Are space agencies concealing data from the Parker Solar Probe's close encounters with the sun? The spark.
Something simple, universal. Hello, welcome to our solar system. We come in peace. Then watch closely. Does it respond? Does its trajectory shift? Does its behavior change in a way that suggests it understood.
Did instruments capture images or spectra of 3I Atlas during the conjunction period that officials chose to withhold? What could possibly motivate such secrecy? Perhaps the comet displayed behavior that defied explanation, challenged core assumptions, or even sparked fear, prompting silence where transparency might have prevailed. Destroyed by oxygen demanding constant energy to function. Yet it's indispensable. Without nitrogenase, there's no way to turn inert nitrogen gas into the ammonia needed for amino acids, nucleotides, and other nitrogen-based molecules life depends on.
Masquerading as a comet to our instruments.
People who grasped the implications might have been unsettled. Perhaps it fragmented in a way that defied natural processes or emitted signals or altered its trajectory, as if under control. Such scenarios, of course, are exceedingly improbable, teetering on the edge of the impossible. Persists endlessly inventive.
Trials on their latest rig chasing break-even with an innovative magnetic scheme. Yet low enough to suggest a hollow structure could be natural, but it's also consistent with an engineered shell. A carbon dioxide ice coating might form naturally, but it's also a practical choice for thermal regulation during an interstellar journey. No single anomaly proves anything, but their convergence is suggestive enough to justify asking the question.
But in minds predisposed to distrust official narratives, the absence of evidence becomes evidence of conspiracy. The psychological role of such theories is well documented. They offer a sense of control, or at least the illusion of it, amid randomness and chaos. They transform a universe of meaningless coincidences into one of hidden order and intent, even if that intent is dark or malevolent. A Atlas rich in nickel and cyanide, scarce in iron. That's a unique starting point. If it's easier, more comforting to believe in conspiracies than to accept that earthquakes strike at random, that comets disintegrate without reason, that we are fragile flickers of consciousness, adrift on a small world racing through an indifferent cosmos. The tale of hidden knowledge and suppressed truth is far more emotionally gratifying than the slow, uncertain story of science, its patient investigations, its cautious steps toward provisional understanding. But here's the thing. Carbon-based life with metal accents, it's metal-based life using carbon as a modifier.
By the early 2030s.
Sometimes the universe really does align in ways that strain belief. Sometimes coincidences feel too precise, too intertwined to dismiss even when causation remains elusive. The October 2025 convergence of events, the solar storm, the comet's disappearance. The earthquakes may well be just that, an astonishing coincidence so improbable it commands our attention, even if in the end. Or it might be the first glimmer of connections we've yet to comprehend, subtle couplings between geophysical systems and space weather operating beneath the limits of our current instruments. Science advances by probing anomalies, not by dismissing them. The researchers studying potential links between solar activity and earthquakes are pursuing legitimate, if admittedly speculative, science. Stable configurations. Some of these configurations spark emergent properties, catalysis, self-repair growth.
We know about the vast emptiness of interstellar space.
They'll probably find nothing, but the search itself is valuable. When 3I Atlas reappears from behind the sun, if it reappears at all, we may not even recognize it. The comet that went in might not be the same one that comes out. And when astronomers publish their analyses offering explanations rooted in physics, chemistry, and orbital mechanics, some will accept those findings and move on. You get selection not biological, but chemical. Others will keep searching for hidden meanings, seeking links between the comet, the earthquakes, and the solar storm that go beyond mere material causation. Both reactions are profoundly human, each revealing our deep need to find meaning in a cosmos that presents more questions than answers. If robots encounter unusual chemistry in Martian soil, say unexpected compounds from 3I Atlas, the AI logs it, perhaps adjusting parameters to boost yields. Not because it grasps the chemistry's significance, but because higher yields align with its efficiency-driven algorithms. Imagine a Martian landscape. The sun unleashed something terrifying, a comet vanished, and the Earth shook, and whatever truth lies beneath those events left us with equal parts wonder and unease. In the sediment ponds and recycling units overlooked in the hum of robotic efficiency. But as the robots grind on processing ever more Martian Earth, these structures accumulate, clustering in waste heaps, pooling in reclamation tanks, whispering of potential. These are no ordinary compounds. They hum with catalytic power. Part 6. The Comet We Can See. While 3I Atlas plays hide-and-seek behind the sun, another comet is putting on a show you can truly witness if you know where to look and are willing to rise before dawn or stay up late after sunset. Together, they weave a tapestry of emergent order, a fusion of Martian dust and interstellar legacy. This symbiosis mirrors a truth etched deep in Earth's own story. Your cells brim with metalloproteins, marvels of molecular machinery, where organic frameworks entwine with metallic. Comet C2025. A6, discovered by the Mount Lemmon Observatory in Arizona, and thus nicknamed Lemon, is nearing its own close encounter with the sun. It's brightening enough to be visible through binoculars or small telescopes, and under dark, clear skies away from light pollution, it might even be seen with the naked eye. Structures born of nickel and 3I Atlas's organic precursors offer catalysis, reactions, hastened efficiencies gained. The robots provide energy structure and intent. The next 2 weeks mark the optimal viewing window. Lemon's perihelion, its closest approach to the sun, is set for mid-November 2025. But the geometry of its orbit means it will reach peak visibility from Earth just before perihelion, when it remains far enough from the sun's glare to be observed comfortably. Not to fuel metabolism, but to streamline manufacturing. Organic molecules, far from encoding genes, fine-tune catalytic sites, amplifying efficiency. This is not life as Earth knows it, nor is it wholly lifeless. It occupies a liminal space. The comet is currently visible in the pre-dawn eastern sky, rising a few hours before the sun. It glows with the soft, fuzzy light, typical of an active comet, featuring a well-developed coma and possibly a short tail. Current magnitude forecasts place Lemon between magnitude 4 and 5, right at the edge of naked eye visibility. Under ideal conditions, the human eye can typically see objects down to magnitude 6, where the line between the engineered and the emergent blurs. Magnitude 4 should be easily visible away from city lights, though spotting it without binoculars demands knowing exactly where to look. The comet is currently traveling through the constellation Cancer, moving eastward against the background stars. Finder charts available online clearly show its path relative to familiar star patterns, making it easier to track. Buy hype to fuel headlines and investor enthusiasm. But then 3I Atlas passed Mars in October 2025. If Musk's timeline holds, robots land 14 months later in late 2026, a narrow window after the comet's nickel cyanide and water vapor settle, freeze into the regolith, and wait. The robots arrive and start digging exactly where those materials landed.
Fully explains why Atlas feels so out of place.
Observing comets calls for patience and dark skies. Unlike planets, which appear as sharp points or disks, comets are diffuse. They spread their light over a larger area. This diffuse nature makes them far more vulnerable to light pollution and sky conditions than compact objects of similar overall brightness. On Earth, that's handy for factories. On Mars, it's critical. Mars has no infrastructure, no roads, no standard equipment, no buildings. Everything must be built from scratch on unpredictable terrain using whatever materials are. A magnitude 4 comet can disappear entirely in bright suburban skies, even where magnitude 4 stars remain visible. Success means traveling away from urban lights to spots where the Milky Way stretches overhead, and the darkness allows your eyes to pick out faint extended objects with low surface brightness. Solar arrays connect batteries and secure a reliable energy supply. No power, no progress. Second priority shelter. Mars is brutal cosmic and solar radiation temperature swings from 25 degrees at night to 20 degrees in daytime sun dust storms lasting weeks. The robots, radiation-hardened and temperature-tolerant, don't need protection. Binoculars are the perfect tool for comet watching. They offer enough magnification to focus the comet's light while maintaining a wide field of view, making it easier to locate and track the object. 750 binoculars, a popular size among amateur astronomers and nature enthusiasts alike, work especially well for this purpose. Sublimate ice and extract it, setting the stage for what comes next.
Set to image Atlas on October 3rd offers a glimmer of hope, but it's limited to surface photography. It can't see inside.
Mount them on a tripod if possible to eliminate handshake and allow for longer, steadier viewing sessions without fatigue. Through binoculars, the comet will appear as a small, fuzzy patch distinctly non-stellar, sometimes tinged with a faint green hue caused by emission from diatomic carbon molecules in the coma. A telescope can reveal even more the structure of the coma potential jets or fans of material erupting from active regions on the nucleus and the tail, if it has developed enough to be seen. Where none should exist, compounds that don't match Martian regoliths expect, but higher magnification comes at a cost. It narrows the field of view, making the comet harder to locate at first and more difficult to keep centered as Earth's rotation slowly shifts the sky. For this reason, many seasoned comet observers prefer binoculars not just for practicality, but for aesthetic reasons. The wide field reveals the comet in context set against star fields and the arc of the Milky Way, highlighting its role as a fleeting visitor drifting through a backdrop of early observations of Lemon revealed something that has comet scientists both nervous and excited. Its brightness wasn't aligning perfectly with prediction models. Comets are famously difficult to forecast because their brightness depends on variables we can't directly measure, like the size of the nucleus, its composition, rotation, state, surface characteristics, and the ratio of dust to gas it releases. Local production is essential, and that means robots capable of reproducing their own kind. Self-replication isn't sci-fi. Earth already has automated factories building cars with minimal human input and 3D printers crafting parts for other printers. The challenge is full autonomy, mining, refining, fabricating, and assembling without human oversight. It's daunting but not impossible, and Tesla is betting on cracking it within a decade. Models rely on assumptions drawn from statistical averages of other comets, but individual comets frequently defy those norms. Lemon has displayed periods of unexpectedly rapid brightening followed by plateaus, where its brightness held steady even as it moved closer to the sun. These deviations could point to a number of underlying phenomena. Efficiency is what the algorithms select for. Here, the line between technology and biology blurs. Self-replication plus selection equals evolution, not biological, but technological. Outburst activity, where fresh volatile material is suddenly exposed, can trigger a temporary surge in gas and dust production, leading to rapid brightening. Additionally, The rotation of the nucleus can bring different hemispheres into sunlight. If one side is more active than the other, this can result in periodic variations in brightness as the comet spins. $20,000, $25,000 each, cheap enough to send thousands to Mars. He also hinted at sentient AI by the late 2030s or early 2040s, not mimicry, but true awareness with self-reflection and goals beyond programming.
To nearby systems. Given the galaxy's age, 13.6 billion years, that scenario feels far from impossible.
Or more ominously, these deviations could signal the early stages of fragmentation, when the nucleus begins to break apart under thermal or tidal stress. Fragmentation is the hidden danger that shadows every comet prediction. A comet might appear perfectly healthy, brightening as expected, on its approach to perihelion, only to suddenly begin disintegrating. The process can unfold abruptly or stretch out over days or weeks, but once it starts, the outcome is rarely favorable for skywatchers.
Distinguishing the artificial from the natural.
Sometimes a large fragment breaks away, forming a separate condensation visible near the main nucleus. Other times, the entire nucleus crumbles into a cloud of small fragments, each too faint to detect individually, but together producing a striking surge in overall brightness as their combined surface area accelerates sublimation. Communicating, coordinating, dividing labor could exhibit collective intelligence. Give that swarm a decade on Mars, access to 3I Atlas's materials, and what emerges. The physics of fragmentation involves a complex interplay of mechanical strength, thermal stress, and spin state. Comet nuclei are fragile, more akin to compacted snow than solid rock held together mostly by their own weak gravity, with a bit of added cohesion from internal ices and possibly sticky organic tars. As the sun heats one side of the nucleus, thermal expansion sets in, creating stress within the structure. Create something neither Earth's life nor human engineering foresaw.
Are we alone?
If the nucleus is spinning, centrifugal forces introduce additional mechanical stress, and outgassing jets can generate torque that gradually spins the nucleus up to faster rotation rates. Eventually, the accumulated stress can exceed the material's strength. Cracks begin to propagate and the nucleus splits apart. In the case of lemon sublimation, science adds yet another layer of complexity. In 14 months, robots will land on soil chemically altered by an interstellar visitor 3I Atlas that left behind a payload of nickel cyanide and water vapor. A gift, a test, or a trap, the comet appears to be driven by carbon monoxide or carbon dioxide sublimation, as much as if not more than water sublimation. These molecules are significantly more volatile than water, meaning they sublimate at lower temperatures and much farther from the sun. A carbon monoxide-driven comet can become active well beyond the snowline, where water ice remains frozen, generating a coma and even a tail while still in the outer solar system. Its outgassing water, carbon dioxide, cyanide, nickel vapor ionizes under solar ultraviolet radiation, feeding a plasma tail that stretches millions of kilometers, swept along by the solar winds 400 to 800 kilometers south flow.
And closest to a massive body like the sun, and you amplify the impact of every ounce of energy you expend.
As the comet draws closer to perihelion and temperatures climb, water sublimation eventually becomes the dominant driver, often triggering a shift in activity patterns and brightness behavior. The interactions between the tail and the solar wind offer yet another fascinating observational opportunity. Mental conditions. Density variations, magnetic field geometries, and wave patterns reflect the comet's activity, a signature traveling at light speed, influencing regions far beyond where Lemon's ion tail, if it develops, one will point directly away from the sun, blown outward by the solar wind like a windsock. Meanwhile, the dust tail traces a curved path composed of particles pushed by solar radiation pressure, but still carrying the orbital motion they had when released from the nucleus. These two tail types, ion and dust, often separate into distinct structures visible in photographs. The dust tail appears yellowish-white, glowing with reflected sunlight. It's broader and more diffuse than the ion tail, curving gently away from the nucleus. Comparing Lemon to 3I Atlas highlights fundamental differences between solar system native comets and interstellar visitors. Lemon formed roughly 4.6 billion years ago within the disk of gas and dust surrounding. Gravitational perturbations from the giant planets eventually scattered it into the Oort cloud, that vast spherical reservoir of comets surrounding the solar system, at distances reaching up to 100,000 astronomical units. Then something, perhaps the gravitational influence of a passing star or a giant molecular cloud, disturbed Lemon's orbit, sending it hurtling back toward the sun on the very journey we are now witnessing. A seed for chemical complexity. Scale this up across millions of dust grains. Its composition reflects the primordial chemistry of our solar system, the isotope ratios and molecular abundances typical of our local region of the galaxy some 4 billion years ago. 3I Atlas, by contrast, formed elsewhere around a different star, under conditions that may have been either similar or radically different. 3I Atlas, or its implications. As robots process these materials, they may amplify the chemistry concentrating nickel and cyanide-derived organics in waste streams or sediment ponds.
It's not impossible, but it's improbably precise, adding another thread to the tapestry of anomalies that make Atlas so intriguing.
The temperature and pressure in that protoplanetary disk, the abundance of heavy elements, the radiation environment, and the timing of planet formation, all these factors shape a comet's composition and structure. By comparing interstellar comets to those from our own solar system, we're essentially examining samples from different stellar nurseries, searching for commonalities that reveal universal processes and differences that spotlight local variations. Reactive sites. Lemon serves as a real-time reminder of just how fragile comets truly are. Every comet is a gamble against disintegration. Most survive their perihelion passage, shedding some mass through sublimation before retreating back to the outer solar system or beyond, still intact. But some fragment, dramatically putting on spectacular shows as multiple nuclei and expanding dust clouds brighten and fade across the sky.
To prop up a geocentric universe? Abandoning dark matter and dark...
A few vanish entirely, destroyed so completely that tracking them afterward becomes impossible. Watching Lemon during its peak visibility isn't just about appreciating a beautiful celestial sight. It's about witnessing a survivor, an object that has endured billions of years in the deep freeze of the Oort cloud, now running a gauntlet of solar heat and radiation that may or may not end in its destruction. The timing couldn't be more fortuitous. But the informational aspect is subtler. Information isn't always encoded in binary or written in code. It can be structural, organizational, the way molecules align, the way energy flows through a system, or the patterns that emerge from countless. While 3I Atlas hides behind the sun, Lemon offers a worthy substitute, a different comet we can actually observe and study firsthand. If you've never seen a comet with your own eyes, if your experience has been limited to images on screens or diagrams in textbooks, now is your chance. As plasma travels through space, it can influence other systems, induce currents, and trigger instabilities that wouldn't otherwise occur. Think of radio waves. Go outside before dawn, find a dark spot, let your eyes adjust for 10 to 15 minutes, and scan the eastern sky in Cancer. That fuzzy patch of light, if you spot it, holds ice formed before Earth existed, organic molecules older than life itself, and silicate dust that predates our planet. Part 7. The Swan and the Context. Comets often seem to arrive in clusters, or at least that's how it appears to those tracking these icy visitors. The reality, however, is more prosaic. Our chemistry and unusual trajectory, those assumptions may not hold. What we do know is that Mars's crustal magnetic fields create pathways. The southern highlands, with their strong, localized magnetic fields, ancient magnetization, locked in the rock. At any given moment, countless comets orbit the Sun at varying distances, most too faint to detect without large telescopes. A handful are bright enough to catch the eye of amateur astronomers, and very rarely one becomes spectacular enough to be visible to the naked eye and capture public imagination. The clusters we perceive alongside Lemon and the vanishing 3I Atlas, another comet designated C2025R2 Swan, has entered the catalog. Swan is named after the solar wind anisotropies instrument aboard the SOHO spacecraft, which observes the sky in ultraviolet wavelengths sensitive to hydrogen emission. Comets produce enormous hydrogen clouds, neutral hydrogen atoms created when water molecules break apart under the Sun's ultraviolet radiation. Third, close approach. Those ions could have circulated, spread, and eventually settled across regions far. These clouds are invisible to optical telescopes, but glow brightly at specific ultraviolet wavelengths, allowing Swan to detect them from vast distances, sometimes spotting comets months before they become visible to ground-based observers. C2025R2 Swan was discovered through its hydrogen corona, that immense invisible cloud enveloping the visible coma. The answer hinges on scale. A few scattered ions likely make no difference. But if the plasma tail was dense enough, if the outgassing was intense, and if the interaction with Mars lasted long enough, the follow-up optical observations confirmed the discovery and enabled precise trajectory calculations. The comet is following an elongated elliptical orbit that will bring it to perihelion in early 2026, well after Lemon's close approach, but soon enough to keep comet observers engaged as they prepare their equipment and observation plans.
Potentials from asteroids, the Moon, or Mars itself. Energy will be a cornerstone likely drawn from vast solar arrays or compact nuclear reactors.
Early brightness estimates for Swan suggest it might reach magnitude 6 or 7 at perihelion, making it primarily a binocular target, but likely not visible to the naked eye, except under exceptional conditions. These predictions hinge on assumptions about the nucleus size and activity level, both of which remain uncertain. Outward, so tails stream behind the comet. A sunward tail defies physics. Some comets discovered by Swan have exceeded expectations, brightening dramatically as they near the Sun. Others have disappointed, remaining faint and diffuse despite hopeful predictions. The only way to know for sure is to watch and wait. One intriguing possibility linked to new comets involves meteor showers. As a comet approaches the Sun, it sheds dust that spreads along its orbital path, creating a stream of particles. Documented. Still, 3I Atlas's anti-tail, paired with its strange chemistry and trajectory, only deepens the mystery of what it left behind on Mars.
All we can do is watch and prepare for the day the Sun's shadow lifts and Atlas reveals its true nature.
If Earth's orbit intersects this dust stream, the particles slam into our atmosphere at high speeds, typically between 30 and 70 km/s, and vaporize in brilliant streaks we call meteors or shooting stars. Most meteor showers we enjoy annually, like the Perseids in August or the Geminids in December, happen because Earth passes through well-established dust trails left by comets that have made multiple perihelion passages, depositing dust over centuries or even millennia. The anti-tail is explainable, not a defiance of physics, just a trick of perspective. But the anti-tail wasn't the only oddity in Hubble's images. Something was missing the dust tail.
The chemistry of a comet reveals clues about the birth of planets. The strange behavior.
New comets making their first journey through the inner solar system can produce unpredictable meteor activity. The dust along their orbits hasn't been evenly spread out by repeated passes and planetary perturbations. Fresh outbursts may create dense clumps of particles, leading to sudden and unexpected meteor displays. And Hubble was primed to capture it. Yet the image revealed only the coma and if Earth happens to pass through one of these dense clumps, meteor rates could spike dramatically, potentially creating a meteor storm, with hundreds or even thousands of visible meteors per hour. Such events are rare and notoriously difficult to predict because they depend on the exact spatial distribution of dust, which we cannot measure directly. Swan's orbit will be calculated with increasing precision in the coming months, allowing astronomers to assess whether any potential intersections with Earth's path through its dust streams might occur. Over weeks, even the mere possibility, however low, of a meteor shower gets comet and meteor enthusiasts buzzing with excitement. Witnessing a meteor storm is a bucket list experience, a celestial fireworks display that might grace the skies only once or twice per generation. These meteors appear to radiate from a point in the sky called the radiant, a visual effect created by the converging perspective of parallel particle trajectories entering Earth's atmosphere. Coma is during a storm, the entire sky seems to rain meteors, streaks of light, shooting in every direction, overwhelming the senses in a way that no photograph can truly capture. But for every comet that brightens and dazzles as hoped, several others fizzle out. The history of comet astronomy is filled with predictions that didn't pan out, objects once expected to become great comets that instead remained faint and unremarkable. Nitrogen reservoir. This anomaly deepens with the comet's water production. At 3.5 AU in late July, when solar flux is low, and Comet Kohoutek in 1973 was predicted to become one of the brightest comets of the century, but barely reached naked-eye visibility, disappointing millions who had been promised a spectacular show. Comet Ison in 2013 was expected to survive perihelion and brighten dramatically, but instead disintegrated. These failures teach humility and remind us just how much we still don't understand about comet physics.
Stars are within reach. Yet, as he points out, we're unprepared for either.
The comparison between Swan and Lemon's brightness curves will ultimately yield valuable scientific insights. Observing two comets simultaneously under similar solar conditions offers a rare opportunity to directly compare activity levels and sublimation physics. Differences in brightness at comparable distances from the Sun reveal variations in nucleus size composition or surface properties, helping scientists unravel the complexities of comet behavior. Swirl in the realm of plausibility, each offering a reason for the comet's prodigious water output at vast distances. Yet none fully unravels the enigma of its steeply climbing production curve.
Targeting systems, we're even more outmatched.
If one comet is water-dominated and the other driven by carbon monoxide, their activity profiles will diverge in distinctive ways. If one fragments while the other remains intact, we gain crucial clues about the structural differences that govern a comet's fragility. Using Swan and Lemon as foils adds a layer of narrative tension. Many comets fail, so will 3 Atlas share that fate. Is there something about the current solar environment that makes comet survival more precarious than usual?
Asking questions, embracing doubt, and building answers that evolve with each new insight.
The October 2025 coronal hole event might have been a singular anomaly, or it could herald a phase of heightened solar activity that imperils any comet venturing through the inner solar system. As the Sun's 11-year activity cycle nears its solar maximum sunspots and coronal mass ejections become more frequent, while solar wind speeds and magnetic field strengths intensify, amplifying the challenges for passing comets. Sparks another, each step amplifying the comets approaching perihelion during solar maximum endure far harsher conditions than those arriving during solar minimum. The history of comet fragmentation offers sobering lessons. Comet Shoemaker-Levy 9's tidal disruption by Jupiter in 1992, culminating in its spectacular impacts in 1994, showed just how completely a comet can be torn apart. By its 2011 return, Comet 73P had shattered into more than 60 identified fragments, creating a sprawling debris field stretching thousands of kilometers along its orbit. Some fragments remained active, generating small comas, while others lay dormant, their volatiles exhausted or locked beneath inactive crusts. These fragmentation events are crucial for assessing and predicting potential space hazards. As it approaches perihelion, this could explain its erratic behavior, multiple active regions, fluctuating outgassing, and unpredictable dust clouds, each fragment contributing its own signature to the comet's glowing coma. Yet fragmentation raises daunting questions about its close encounter with Mars.
This response. Without such a structure, we're improvising in the face of a potentially existential event, a recipe for chaos. Decades passed, and the WOW signal faded into a curious historical artifact, referenced in SETI literature but rarely driving active research. Then, in 2020, 3I Atlas arrived stage 3 physical proof. A tangible object, we could study its strangeness unfolding under scrutiny, a composition that defies typical cometary or asteroidal profiles, an orbit that resists tracing to any parent star, and a trajectory that aligns eerily with the WOW signal's origin in Sagittarius. If this is choreography, it's patient operating on timescales that span human generations.
Most comet fragments harmlessly blaze out in the atmosphere or bypass Earth altogether. Yet the risk landscape shifts dramatically when facing dispersed debris instead of a lone object. Foreshadowing the 60 comet event destined to be the brightest comet spectacle of the century casts current observations into sharp perspective. Comets are the solar system's chaotic clockwork, arriving unpredictably, flaring with erratic brilliance, and they mark time in human consciousness, unlike the steady rhythms of planets and stars. One generation recalls Halley's Comet in 1986, a view that disappointed many but left a lasting cultural imprint. The generation before witnessed Comet Hale-Bopp in 1997, dazzling the naked eye for months and shining bright enough to be seen from city centers. Today's generation might remember Lemon Swan or 3I Atlas. Are we currently in a cluster period of unusual comet appearances? Statistical analyses of comet discovery rates over decades reveal fluctuations that could indicate genuine clustering, or they might merely mirror advances in detection technology. With more telescopes sweeping wider skies at ever greater sensitivities, it's only natural that more comets are being found.
The edges of knowledge carry these responsibilities keenly, even as public debates often paint technology as either a savior or a scourge. The reality is more.
The Atlas survey, which discovered 3 of the Atlas comets, was designed specifically to detect near-Earth objects with comets as a fortunate bonus. Alongside it, the Catalina Sky Survey, Mount Lemmon Observatory, and Pan-STARRS in Hawaii. All operate automated systems that vigilantly scan the skies for anything in motion. And since comets move, but there's a tantalizing hint in the data that the Oort cloud, the distant reservoir of comets, might undergo perturbations that send showers of comets plunging toward the inner solar system. Passing stars, gravitational tugs from giant molecular clouds in the galaxy, and even the solar system's vertical oscillation through the galactic plane as it orbits the Milky Way's center, all these forces could shake comets loose to the comet's growing list of oddities.
To become a saga written across.
If real, these comet showers would unfold over timescales of millions of years, far too vast for direct human observation. Yet hidden within the geological record traces of clustered impacts might reveal these ancient storms of comets that pummeled the inner solar system during the reign of the dinosaurs or even earlier in Earth's history. This polarization hinting at dust unlike anything we've seen. And all this from an interstellar wanderer that grazed Mars with uncanny precision 2 years before our robots touched down there.
And unfolding story. Until next time, wherever you are, whatever hour it is, good night. Pitted against a chorus of skepticism that ranges from measured critique to outright derision.
Comets serve as the solar system's chaotic clock, precisely because they defy the regular, predictable paths that planets follow. While most planets travel along nearly circular orbits, allowing their positions to be calculated centuries ahead, with remarkable accuracy, comets emerge from the outer darkness on highly elliptical trajectories. And strangeness. Yet the strangeness forms a pattern, as if 3-eye Atlas were crafted to confound, offering just enough natural clues to avoid being labeled artificial. Their return times, if they return at all, span decades, centuries, or even millennia. Some are newcomers, first-time fallers from the Oort cloud. Others are short-period comets captured by Jupiter's gravity into orbits that bring them back every few years. They remind us that the solar system is not a clockwork mechanism of perfect orbits, but a dynamic, chaotic arena where gravitational forces constantly reshuffle trajectories and new players arrive without warning. Operation, digging deeper, processing the chemistry, activating something profound. Part 8. The Unbreakable Signal. While astronomers scan the skies for comets and monitor the solar wind, another cosmic race unfolds in laboratories and ground stations here on Earth. In 2025, China announced the completion of the world's longest quantum communication link, a 12,900-kilometer network connecting Beijing to distant ground stations via satellite relays, and claimed the system offers effectively unhackable data transmission. And lunar rocks. A gas and dust cloud collapsed its core, igniting as the sun, its outer disk, flattening into planets over mere millions of years. By 4.5 billion years ago, the announcement represents a milestone in the quantum information revolution. If the system performs as advertised, it will reshape the landscape of global communications and cybersecurity in ways that reach far beyond immediate military or commercial applications. At its core, quantum key distribution exploits fundamental principles of quantum mechanics to detect any attempt at eavesdropping. Elements, less carbon, oxygen, or iron, with potentially skewed elemental ratios in some regions. The modeling of 3-eye Atlas's velocity relative to the local standard of rest, the average motion of stars near us, suggests it hails from the Milky Way's thick disk, a realm of older metal-poor stars formed when the galaxy was young. If 3-eye Atlas was born around such a star, it could indeed be 7 to 10 billion years old.
Part 11. AI and the Cosmic Hunt. In 2025, artificial intelligence achieved what human astronomers had struggled with for decades. It uncovered subtle patterns in stellar motion data, revealing previously undetected close encounters between the Sun and nearby stars millions of years ago. Machine learning algorithms trained on the Gaia Data Release 3 catalog, containing positions and velocities for over 1 billion stars, reconstructed orbital trajectories backward through time.
The quantum no-cloning theorem guarantees that these states cannot be perfectly copied. Any attempt to measure or intercept the photons inevitably disturbs them in ways that can be detected. This allows two parties sharing a quantum communication channel to generate encryption keys and be absolutely certain if anyone tried to intercept those keys during transmission. 2. A signature that could point to its birth in a low metallicity environment where oxygen was scarce. In such a realm, chemical equilibrium might favor CO and CO2 over H2O, with ices condensing in a protoplanetary disk around a metal-poor star, yielding compositions alien to our local neighborhood.
To the alien hypothesis, a move they decry as sensationalism that erodes the credibility of legitimate astronomical research.
The process begins with entangled photons, pairs of particles created simultaneously, sharing a quantum connection, so that measuring one photon instantly influences the other, no matter the distance between them. This phenomenon, famously dubbed spooky action at a distance by Einstein, has been confirmed through countless experiments and underpins several emerging quantum technologies, including quantum computing and quantum teleportation. Civilizations in our galaxy hinges on a critical variable: how long such civilizations endure. A century, 1,000,000 years, longer. We don't know. But 7 billion for quantum key distribution. Entangled photons enable two parties to establish shared random numbers that serve as encryption keys. Implementing this hardware demands extraordinary precision. Photons must be generated, entangled, transmitted, and detected with minimal loss and maximum fidelity. Optical systems must align satellite transceivers with ground stations across hundreds or even thousands of kilometers, all while compensating for atmospheric turbulence, satellite motion, and Earth's rotation. This is where the Bracewell probe hypothesis enters the frame. Rather than broadcasting fleeting radio signals that fade with distance, an advanced single-photon detectors must register individual particles arriving at rates of thousands or even millions per second, distinguishing genuine signals from background noise and detector dark counts. Error correction protocols handle inevitable imperfections while still ensuring security. China's system relies on the Michus satellite launched in 2016 and named after an ancient Chinese philosopher, letting time work its magic. Imagine a civilization 7 billion years ago, masters of their star system, perhaps even orbiting at roughly 500 kilometers altitude. The satellite follows a sun-synchronous path that provides regular communication windows over ground stations. During each pass, lasting several minutes, it distributes entangled photons to pairs of ground stations, enabling them to establish shared encryption keys. Might lie dormant. But if life emerges, or if an intelligent species arrives and stirs the environment, those materials awake. These keys then secure conventional data transmission through standard encryption algorithms, with the quantum channel ensuring the keys themselves remain uncompromised. The recent expansion to 12,900 kilometers marks a significant engineering breakthrough, surpassing earlier demonstrations that covered shorter distances or depended on trusted relay stations. The new system links quantum channels across multiple satellite passes and ground stations, establishing end-to-end security on a continental scale. According to Chinese researchers, the network already serves government and financial institutions, safeguarding communications against both present and future decryption threats. And that last point is crucial. A civilization launching millions of probes, each aimed at a different star system, isn't banking on pinpoint accuracy. It's playing a numbers game. Most probes might drift through empty voids, barren systems, or current encryption systems, those protecting everything from bank transactions to classified government communications, depend on mathematical problems that are computationally hard for classical computers to solve, such as factoring large numbers or computing discrete logarithms. Stirred by spacecraft or energy production. If 3I Atlas is a probe with autonomous sensing, it might have detected our electromagnetic chatter, our radio waves, our satellites, and made a minute course correction. A nudge of mere meters per second, amplified over millions of years, could steer it from the solar system's fringes to its inner heart. Such a feat is these tasks demand such immense computational time that breaking encryption is practically impossible, even with the fastest supercomputers today. But quantum computers, if scaled up sufficiently, could solve these problems efficiently, rendering current encryption methods obsolete. Data encrypted now and intercepted by adversaries could be decrypted years or decades later once quantum computers reach maturity. Times has Earth been touched by interstellar gifts, isotope studies of our oceans. Quantum key distribution offers protection against this harvest. Now decrypt later threat because its security is rooted not in computational difficulty, but in fundamental physics. Western nations, especially the United States and European countries, watch China's advances in quantum communications with growing concern.
The principle of Occam's razor favoring the simplest explanation leads critics to conclude it's just an interstellar comet, a fascinating object worthy of study, but ultimately a product of natural processes, not alien engineering.
The MIT Technology Review Quantum Index in 2025 ranks China ahead in several quantum technology metrics, including quantum communications and quantum sensing. Meanwhile, American research programs are striving to catch up, backed by Department of Energy funding quantum network testbeds and DARPA's exploration of space-based quantum communication architectures. Worlds below their arrivals sinking by cosmic whim or cunning intent with eras of profound upheaval. Pivotal thresholds where a planet teeters, but China's early lead, fueled by substantial government investment, has created a quantum gap that alarms defense planners and technology strategists alike. The policy implications reach far beyond mere technological rivalry. If quantum communication networks become the backbone of future secure communications, nations lacking access to this technology risk facing a significant information disadvantage. What lies ahead, the cosmic clock, ticks relentlessly forward. We stand now in a breathless pause. In mid-October, through Atlas slipped behind the sun, cloaked in its blinding inferno, hidden from Earth's gaze for weeks. International agreements governing quantum technology development remain absent. Questions about export controls, technology transfer, and standardization are still unresolved. Some researchers advocate for open collaboration and the shared development of quantum networks as global infrastructure, much like how the Internet evolved into an international resource, turned from the sun's veil in early December. By then it will drift outward, slipping from our reach. The spectacle may dim, others push for competitive advantage and restricted access, viewing quantum superiority as a strategic asset too valuable to share. Could space-based quantum networks become the backbone of the future Internet? The vision involves constellations of quantum satellites, providing global coverage ground stations in every major city, and quantum repeaters extending the range beyond direct line-of-sight limits. Or a hybrid of nature and design, then perihelion. Data would travel encrypted with quantum keys that refresh continuously, immune to interception, and resistant even to future technologies we haven't yet imagined. This system would integrate seamlessly with existing fiber optic networks, creating a hybrid classical quantum infrastructure, where quantum channels distribute keys and classical channels carry the bulk of the data. Communication lines choked. Its primary dish, repurposed as a solar shield, faces the sun for protection, forcing reliance on a weaker backup for data transmission. Conspiracies naturally arise around technologies this advanced and this secretive. Quantum key distribution systems demand extensive testing and calibration, producing data on photon transmission statistics, detector efficiency, and error rates. Yet most of this information remains classified or proprietary. Chinese publications describe the system's capabilities in broad. Western intelligence agencies undoubtedly monitor the program closely, using signals intelligence and other methods to assess its true capabilities against public claims. This opacity fuels speculation about whether the system functions as advertised or if undisclosed vulnerabilities exist. Some are particularly concerned about the potential for state surveillance, fearing the system could be used to monitor or control communications on a global scale, to avoid igniting confusion. A faint signal, not definitive but provocative enough. A government controlling a nationwide quantum communication network would have unprecedented power to monitor who communicates with whom, even if the content remains encrypted. Metadata. The information about communication patterns, rather than the content of the messages, often reveals as much, if not more, than the messages themselves. This raises significant concerns about privacy and state surveillance.
And more like something engineered, designed with structural integrity, to maintain stability in the face of dynamic forces.
Traffic analysis has the power to uncover social networks, monitor movements, and predict behavior with astounding precision. Imagine a quantum network that logs every connection, every photon transmission, and every key generation event, forming a surveillance infrastructure of unprecedented scale. This concept aligns closely with the 3-Eye Atlas narrative, drawing an intriguing parallel between the two. Knack for throwing curveballs, technical glitches, funding snags, regulatory mazes. Just as comets deliver messages from distant star systems, encoded not in language but in chemical signatures and isotope ratios, humans are now constructing systems to carry unbreakable encoded messages across our own planet. Both serve as vessels for information that endures even the most hostile environments. Comet chemistry survives the vacuum of interstellar space and the intense heat of the sun, while quantum keys endure the efforts of active adversaries attempting to intercept them. Both push the limits of what's possible. Comets, as natural carriers of information, have been shaped by billions of years of cosmic physics. Quantum networks, as human-engineered carriers, have evolved over decades of precise innovation. Yet countless unknowns still remain, each one presenting new challenges and discoveries waiting to unfold. Something profound, not mere traces but a payload's current quantum key distribution rates, typically measured in kilobits per second, lag far behind the blazing speeds of classical communication, which are measured in gigabits or even terabits per second. To scale quantum networks to handle internet-level traffic, we'll either need significant breakthroughs in photon transmission and detection efficiency, or we'll have to explore entirely new approaches to quantum networking. Or whether their synergy conjures something utterly unexpected, chemistry that dances on the edge of the unknown. The timeline unfurls with precision. December 2025, ground-based telescopes pierce the dawn sky, capturing 3-Eye Atlas as it emerges from the sun's decoherence, the phenomenon where quantum properties are lost due to interactions with the environment, imposes fundamental limits on how long quantum states can be preserved and how far they can be transmitted. Satellites offer a solution by operating in the vacuum of space above much of the atmosphere, extending the range. However, atmospheric turbulence at ground stations continues to degrade performance, presenting an ongoing challenge. Streams back whispering of anomalies, nickel spikes, where none belong, organic compounds blooming in barren wastes. From 2030 to 2035, targeted missions zero in confirming endpoint security introduces another significant challenge. While quantum key distribution ensures the secure transmission of keys, these keys must eventually be used by classical computers to encrypt and decrypt data. If those computers are compromised, whether through malware, physical access, or side-channel attacks that exploit electromagnetic emissions or power consumption, then even the most secure quantum keys become meaningless. Ultimately, security is only as strong as the weakest link in the chain. On its chemistry, a silent partner, in any real system, weak links are bound to proliferate. The quantum space race narrative reflects a deeper truth about human nature and technological progress. We compete even when it comes to understanding and harnessing the fundamental laws of physics. Quantum mechanics, perhaps the most successful physical theory in terms of predictive accuracy and technological impact, transforms into a weapon in geopolitical competition as nations vie to unlock its full potential for power and influence.
Its defining moment.
The very quantum principles that reveal the secrets of atomic structure and chemical bonds are now safeguarding our communications and unlocking the door to groundbreaking computing power. Nations are pouring billions into quantum research, not merely driven by scientific curiosity, but because the future of military dominance and global economic leadership may hinge on the advancements of quantum technology in the decades to come. Reappears is the fulcrum. Its post-perihelion state compared to pre-perihelion data will speak volumes. Did it survive the sun? As the race intensifies, unanswered questions loom. Does competition fuel innovation more rapidly than collaboration? Will the benefits of quantum networks be distributed globally? Or will they remain concentrated in a handful of technologically advanced nations? These uncertainties persist even as the race accelerates. The case of robust evidence might dismiss it as a hoax or conspiracy fueled by distrust in institutions.
Can yield a dramatic change in trajectory. For a spacecraft, this would be the ideal moment to execute a course correction shielded from Earth's prying eyes by the sun's glare. We won't see it happen. No telescope, no matter how advanced, can pierce the corona to witness a maneuver in real time. The sun's brilliance ensures Atlas's actions, natural or artificial, remain cloaked. This idea, while bordering on science fiction, is compelling because it ties together multiple cosmic mysteries, untraceable interstellar objects, the enigma of dark matter, and the challenge of efficient interstellar travel. If dark matter has properties, we've yet to detect interactions beyond gravity that our experiments aren't designed to capture probes built by civilizations. Mastering those properties could move in ways that defy our
The potential applications of this discovery span across medical, ecological, and even industrial fields, while its deeper implications challenge our understanding of waste value and the incredible adaptability of biological systems. By reprogramming these systems, one substance can be transformed into another in ways previously unimaginable. Urea, the primary nitrogen-containing compound in urine, serves as a waste product in mammalian metabolism. Yet it now holds the key to this innovative. When proteins break down in the body, amino acids are metabolized, and the nitrogen they contain must be excreted. Aquatic animals have a simple, energetically inexpensive solution. They excrete ammonia directly, which is easily diluted and carried away by water. However, land animals face a more significant challenge. While ammonia is toxic and accumulates quickly, water conservation is crucial. As a result, terrestrial animals, birds and reptiles excrete uric acid, a relatively insoluble compound that precipitates out and can be expelled as a paste-reducing water loss. Mammals, on the other hand, produce urea, which is soluble enough to be transported in water but less toxic than ammonia. This results in liquid urine, a compromise that balances water conservation with efficient waste removal.
The antenna means data transmission will be slow, with detailed results potentially not reaching Earth until February 2026. Patience will be required, but the payoff could be profound.
Humans typically produce between 1 to 2 liters of urine daily, depending on fluid intake and metabolic rate, containing approximately 20 to 30 grams of urea. Over the course of a year, this adds up to about 10 kilograms of urea per person. With a global population of 8 billion people, this results in around 80 million metric tons of urea being excreted annually. Currently, this urea either enters sewage systems, is broken down by bacteria. The new synthetic biology approach explores whether this waste stream could be converted into something valuable. Hydroxyapatite. The mineral component of bones and teeth is a calcium phosphate compound with the formula Ca10PO4,6OH2. It provides bones with the hardness and structural integrity necessary to support body weight and protect organs.
And scrutinizing every detail for anything that deviates from the comet model. Could there be a glint of something metallic? A faint radio signal? A geometric structure that defies natural formation? These observations could tip the scales, either reinforcing the natural explanation or lending credence to Loeb's hypothesis.
Natural bone is a composite material with hydroxyapatite crystals embedded in a collagen protein matrix. This combination merges the hardness of the mineral with the flexibility and toughness of organic fibers. For medical applications, pure hydroxyapatite is required for bone grafts, dental implants, and reconstructive surgeries.
Data on its properties. This encounter could catch details missed earlier, a last opportunity to confirm or challenge our understanding. After this, Atlas's path diverges.
Currently, hydroxyapatite is synthesized through chemical processes or harvested from animal bones. But both methods face limitations in terms of purity, crystal structure, and production costs. The engineered yeast approach, however, presents a promising alternative through metabolic pathway engineering. Researchers have identified the series of enzymatic reactions required to convert urea into the chemical precursors of hydroxyapatite, and have successfully inserted the genes encoding these enzymes into yeast cells. Mere outliers, or is the universe revealing a strangeness we've only begun to grasp?
The possibility, however remote, that it might respond stirs the imagination and underscores the stakes.
The yeast Saccharomyces cerevisiae, commonly used in brewing and baking, now carries synthetic metabolic pathways that don't naturally exist. When fed urine as a nitrogen source, along with calcium and phosphate ions, these engineered yeast cells produce hydroxyapatite crystals. These crystals then precipitate out of the solution, allowing them to be harvested efficiently. Modest setups to sprawling cubic kilometer giants. Gravitational wave The mechanism behind this process involves multiple steps. Urease-UR's enzyme breaks urea into ammonia and carbon dioxide. The ammonia is then incorporated into amino acid synthesis pathways, while the carbon dioxide, along with additional calcium and phosphate ions, undergoes mineralization reactions that form hydroxyapatite. Simultaneously, the universe keeps startling us, not because it's changed, but because we're finally seeing it clearly.
be to encounter something artificial.
The crystallography of the resulting hydroxyapatite. Its size, shape, and purity depends on various reaction conditions, including pH, temperature, ion concentrations, and the genetic programming of the yeast pathways. Early results show promise with hydroxyapatite produced that exhibits properties similar to bone mineral. However, significant optimization is still needed before the process can be applied in medical applications. Instrument glitches get mistaken for signals. False positives abound.
Picture.
Currently, the efficiency and yield rates of this process limit its immediate viability. The yeast produces hydroxyapatite at concentrations too low for commercial use, meaning that large bioreactor volumes are required to generate meaningful quantities. Further improvements in efficiency and scaling are necessary to make this process commercially viable. But it's one object, that neutrino, a single event. Are they linked? Purification challenges arise because hydroxyapatite must be separated from yeast cells, growth medium components, and metabolic byproducts. Purity is crucial for medical applications, as any foreign proteins or bacterial endotoxins in implanted hydroxyapatite could trigger immune responses or infections. Achieving medical-grade purity from a biological production system necessitates rigorous quality control.
This leads to a startling possibility. Extraterrestrial civilizations might be communicating constantly through a galaxy-wide quantum network connecting thousands or millions of nodes. And we'd never know. Unlike radio signals which leak photons, detectable by any receiver, quantum communication leaves no classical signature.
Each of these options has its drawbacks. Autografts require additional surgery to harvest the graft tissue, increasing the risk of complications. Allografts carry small risks of disease transmission and immune rejection. Synthetic ceramics sometimes fail to integrate well with natural bone, limiting their effectiveness. Familiar, yet never stops feeling alien.
Ideas uncritically or rejecting them reflexively, but about observing meticulously, measuring precisely, and analyzing honestly.
Hydroxyapatite produced biologically from waste materials could offer an abundant, cost-effective alternative if the challenges of production and purification are addressed. One major market for this material is dental implants. Hydroxyapatite coatings on titanium implants significantly improve osseointegration, which is the bonding between the implant and the jawbone. Overreaching, seeing patterns in randomness, letting imagination outrun evidence.
Of the puzzle. By the end of the year, we'll have a clearer picture of what Atlas is, a comet, or something far more extraordinary.
Currently, these coatings are made using hydroxyapatite, produced through high-temperature chemical processes, which are energy-intensive. In contrast, biological production at room temperature in aqueous solutions would not only reduce energy costs and the carbon footprint, but could also lead to the creation of more bone-like crystal structures that integrate better with living tissue. The ecological benefits of this process extend beyond the direct use of the material itself, offering a more sustainable and environmentally friendly alternative.
Day, when it emerges, we'll know a little more about our place in the universe and the possibilities that await us.
Urea in wastewater contributes to eutrophication when released into rivers and coastal waters. Excess nitrogen from urea stimulates algal growth, leading to blooms that deplete oxygen and create dead zones. Capturing urea and converting it into solid mineral hydroxyapatite removes nitrogen from the wastewater stream, reducing its environmental impact. This process embodies waste valorization, the principle of treating waste as a resource rather than a disposal problem.
And remember, The universe has surprised us before, and it will undoubtedly surprise us again.